Imagine this. You're sitting in the cockpit of humanity's most advanced spacecraft. The countdown is running. 3, 2, 1, ignition. In the next second, you shoot into space, faster than any airplane, any rocket, anything we have ever built. And then something completely incomprehensible happens. You feel nothing. No speed, no pressure, no force, even though you are in the process of tearing apart the laws of physics. But before you even understand what is happening, one question forces itself into your mind, a question that decides over life and death. What happens when, at half the speed of light, a speck of dust crosses your path? The answer is so terrifying that it calls into question everything we thought we knew about space travel. Let's begin. Part 1. The journey begins, and first optical effects, acceleration and speed perception. Picture this. You're strapped into the cockpit of humanity's most advanced spacecraft, engines humming beneath you, ready to push the boundaries of physics itself. The countdown echoes through your helmet. 3, 2, 1, ignition. And just like that, you're accelerating away from Earth, leaving behind everything you've ever known. But here's where things get interesting, and I mean really interesting. As your spacecraft picks up speed, blasting through the cosmos at velocities that would make a fighter jet look like it's standing still, you'd expect to feel something, right? The overwhelming rush of speed, maybe. Your body pressed back against the seat from the sheer velocity. Here's the mind-bending truth. You feel absolutely nothing from the speed itself. Zero, zilch, nada. Think about it this way. You're sitting right now, probably thinking you're perfectly still, but you're not. You're on Earth, which is spinning at about 1,000 miles per hour at the equator. At the same time, Earth is orbiting the Sun at roughly 67,000 miles per hour, and the entire solar system, it's racing through the Milky Way at 500,000 miles per hour, yet you can't feel any of it. You're sipping your coffee without a care in the world. Speed, by itself, is completely undetectable to the human body. What you actually feel is acceleration, the change in speed. Inside your spacecraft, if the engines are providing a constant, gentle push, let's say equivalent to Earth's gravity, you'd feel like you're just sitting in a comfortable chair. You could be moving at 99% the speed of light, and as long as you're not changing that speed, you'd feel no different than sitting in your living room. Remember those times when you've been on a smooth flying airplane? Once it reaches cruising altitude and stops climbing, you can walk around, pour a drink, read a book. You're traveling at 500 miles per hour, but it feels like you're stationary. That's because speed is relative. From your perspective inside the plane, you are stationary, and it's the ground moving past you. The same principle applies in our spacecraft, even at relativistic speeds. But here's where the universe throws us a curveball. While speed itself might be comfortable, there's one terrifying risk that comes with high-velocity travel: collisions. At the speeds we're discussing, even a speck of dust becomes a weapon of mass destruction. Imagine a grain of sand, smaller than the period at the end of this sentence, hitting your spacecraft while you're traveling at half the speed of light. The kinetic energy would be absolutely devastating, potentially vaporizing your entire ship in a microsecond. We're talking about energies comparable to nuclear detonations, all from something you wouldn't even notice if it landed on your hand, a pebble. That would be like getting hit by multiple atomic bombs simultaneously. This is why our hypothetical spacecraft needs some serious protection. Something like an advanced electromagnetic field that can deflect or vaporize incoming particles before they reach the hull. Without it, high-speed space travel would be a one-way ticket to oblivion. The gathering of stars, light aberration, Now, as your spacecraft continues to accelerate, something strange starts happening to the view outside your window. The stars, those distant points of light scattered across the cosmic canvas, begin to move. Not randomly, but in a very specific pattern. The stars in front of you, in the direction you're traveling, seem to drift closer together. It's as if the entire forward sky is contracting, gathering into a tighter and tighter cluster. At first, the effect is subtle. Maybe you think it's just your imagination, or perhaps a trick of the window. But as you continue to accelerate, the phenomenon becomes undeniable. Stars that were once spread across a wide angle of your forward view now appear packed into a smaller region. Meanwhile, behind you, the opposite is happening. The stars seem to spread apart, the sky appearing to expand and widen. This isn't science fiction. This is a real optical effect called the aberration of light. And to understand it, let's use an everyday analogy that'll make it click instantly. Imagine you're driving your car on a perfectly calm day, and suddenly it starts to rain. When you're stopped at a red light, the rain falls straight down, hitting the roof of your car. Gravity pulls each drop vertically downward, and that's exactly how you see it. But now you start moving. You accelerate up to highway speeds, let's say 60 miles per hour. Look at your windshield. What do you see? The rain isn't falling straight down anymore, at least not from your perspective. Instead, the raindrops appear to be coming at you from the front, hitting your windshield almost horizontally. The faster you drive, the more horizontal the rain seems to become. If you could somehow accelerate to incredible speeds, the rain would appear to be coming straight at you from directly ahead, even though it's still falling vertically from the clouds. The same exact thing happens with starlight. Light from those distant stars is traveling through space in specific directions. But as you accelerate towards some stars and away from others, the direction from which you receive that light changes. Stars ahead of you appear to shift forward in your field of view. Their light seems to come more and more from directly in front of you, as if they're gathering together in a central point. What you're experiencing here is how motion affects your perception of light's direction. Light has a constant speed, roughly 186,000 miles per second. But when you're moving relative to the source of that light, its apparent direction changes. This is pure physics, and it's happening every single time you move, even when you're walking down the street. It's just too subtle to notice at everyday speeds. The faster you go, the more dramatic this aberration becomes. At 10% the speed of light, stars would noticeably cluster forward. At 50%, the effect would be striking, with your forward view looking significantly compressed. And as you approach the speed of light itself, well, we'll get to that mind-blowing scenario later. Changes in field of view. As this stellar gathering continues, another fascinating effect kicks in. And this one has everything to do with the intensity of light itself. Remember, light carries energy, and when you're moving toward a light source at high speed, something remarkable happens. You intercept more of that light in a given amount of time. Think of it like this. Imagine you're standing in a field and someone is throwing baseballs toward you at a steady rate, say 1 ball per second. If you stand still, you catch 1 ball every second. Simple, but now, what if you start running toward the person throwing the balls? Suddenly, you're catching balls more frequently because you're moving into them. You might catch 1 ball every half second instead. The rate of ball throwing hasn't changed, but your motion has changed how frequently you encounter them. Light works the same way. As you accelerate toward stars in front of you, you're intercepting more of their photons per second. More photons mean more light energy, and more light energy means increased brightness. The stars ahead of you don't just gather together in your field of view, they also become more intense, glowing brighter and brighter as you accelerate. But wait, there's more. Behind you, the exact opposite is happening. Stars in your rear view are becoming dimmer and dimmer. Why? Because you're racing away from their light. Fewer photons reach you per second, resulting in decreased intensity. The backward sky doesn't just expand, it also darkens, fading toward black. This creates an increasingly asymmetric view of the universe. Ahead, compressed, brilliant, intensely bright. Behind, expanded, dim, descending into darkness. You're creating your own personal division of the cosmos, split between a dazzling forward sphere of starlight and a darkening void behind you. And here's where it gets even stranger. This isn't just about brightness. The aberration of light is literally changing your entire perspective on the universe's geometry. The normal spherical distribution of stars around you is being warped into something completely different. A teardrop-shaped field of view with everything compressed forward and stretched backward. The bending of the space grid. To really visualize what's happening to your perception of space, let's do a thought experiment. Imagine the entire universe is overlaid with a three-dimensional grid, like a cosmic graph paper, extending infinitely in all directions. Each line is perfectly straight. Each intersection forms a perfect right angle. This grid represents the fabric of space itself, the arena in which all motion and matter exist. Now, when you're at rest relative to this grid, everything looks normal. Looking forward, you'd see the grid lines converging toward a distant vanishing point due to perspective, just like railroad tracks appearing to meet at the horizon. The lines are straight, the geometry is familiar, everything makes intuitive sense. But start accelerating and watch what happens to this grid. As the aberration of light takes hold, those perfectly straight lines begin to curve. The grid in front of you appears to compress and bend inward, as if space itself is being squeezed. Lines that should be parallel seem to bow toward each other. The neat, orderly structure of space appears to warp and distort. This is the visual manifestation of something called Terrell-Penrose rotation, named after the physicists who first described this peculiar effect. As you move at relativistic speeds, objects don't just appear contracted in the direction of motion, they actually appear rotated. It's as if you're seeing them from a different angle, even though your actual viewing angle hasn't changed. Imagine passing by a massive cube floating in space. Common intuition might suggest it would look squashed, compressed in the direction you're traveling. But that's not quite right. Instead, the cube would appear tilted, rotated toward you. You'd see faces of the cube that should be hidden from your view. The object's geometry appears twisted in space, as if the universe is showing you multiple angles simultaneously. This happens because light from different parts of an object takes different amounts of time to reach your eyes. When you're moving very fast, light from the back of an object has farther to travel to catch up with you than light from the front. So you receive these light rays at different times, but your brain processes them simultaneously, creating this apparent rotation effect. The bent grid, the curved lines, the tilted objects, all of these are telling you something profound. Motion doesn't just change where things are, it changes how space itself appears to be structured. Your perspective on the geometry of the universe is fundamentally altered by your velocity through it. Changes in object appearance. As you continue your journey, accelerating past planets, asteroids, and other cosmic structures, you'd notice that every object you pass exhibits this strange rotational appearance. A spherical planet wouldn't look quite spherical anymore. Its edges would seem compressed in your direction of motion, giving it an elongated, almost oval appearance from your perspective. But here's the crucial thing to understand. This is still an optical effect, a quirk of how light reaches your moving eyes. The planet itself hasn't actually changed shape. An observer at rest relative to the planet would see it as perfectly spherical. But from your high-speed reference frame, light rays are reaching you in such a way that the planet's appearance is transformed. Imagine flying past a massive space station, a cylindrical structure rotating slowly in the void. From your ultra-high-speed perspective, you wouldn't see it as a simple cylinder. Instead, it would appear stretched and rotated, with dimensions that seem impossible, contradictory even. You might see parts of the structure that should be completely hidden from your line of sight. The faster you go, the more extreme these distortions become. At speeds approaching light itself, objects would appear radically transformed, their shapes bearing little resemblance to their rest frame geometry. A simple rectangular building might look like a twisted, bent structure, angles appearing skewed, parallel lines seeming to converge at impossible points. This is perspective on steroids, perspective amplified by relativistic speeds to create visual effects that seem to defy logic. But they don't defy physics. They're the inevitable consequence of combining finite light speed with extreme relative motion. What's truly fascinating here is that these effects work both ways. If someone were watching you from a stationary position as you blazed past them at near light speed, you and your spacecraft would appear contracted and rotated to them as well. You might look like you've been compressed to a fraction of your normal length, squeezed like an accordion in the direction of your motion. Yet inside your spacecraft, you feel completely normal. You look at your hands, they appear perfectly ordinary. You look at your crewmates, they look fine. There's no sensation of being compressed or rotated. That's the beauty and the strangeness of relativity. These effects are entirely dependent on the observer's reference frame. Who's right? The person who sees you compressed, or you who feels normal? Both are. That's not a cop-out answer. It's a fundamental truth about the universe. There is no absolute perspective, no universal frame of reference from which to judge. Every observer's measurements are equally valid in their own reference frame. As your acceleration continues, these optical effects pile up, layer upon layer, creating a view of the universe that would be utterly alien to anyone who's only ever moved at ordinary speeds. The stars cluster forward, objects rotate and distort, brightness shifts dramatically between forward and backward views. You're witnessing the universe through a high-speed lens, and what you're seeing is reality revealing its relativistic nature. But these are just the beginning. These optical effects, as dramatic as they seem, are only the appetizers. The main course, the truly reality-bending phenomena, are still ahead. Because up to this point, everything we've discussed is reversible. If you were to slow down and return to Earth, these effects would simply reverse, leaving no permanent changes. The real magic, the stuff that permanently alters your experience of space and time, only kicks in when you truly approach the speed of light. That's when special relativity stops being just an interesting optical curiosity and becomes a fundamental restructuring of reality itself. And trust me, what's coming next will challenge everything you thought you knew about time, distance, and the nature of the universe. Are you ready to go even faster? Part 2. Doppler effect and time delays. The principle of looking into the past. Here's something that'll blow your mind. Every single time you look at anything, you're literally seeing the past. Not metaphorically. Actually, genuinely looking backward in time. Right now, as you look at the wall across the room, you're seeing it as it was a few billionths of a second ago. The light bouncing off that wall took time to reach your eyes, and during that journey, time passed. Admittedly, it's such a tiny fraction of a second that it's completely irrelevant for everyday life. But the principle, that principle is absolutely fundamental to understanding our universe. Now scale this up, way up. Look at the moon on a clear night. That pale, silvery light you're admiring. It's about 1 1/3 seconds old by the time it hits your retina. You're not seeing the moon as it is right now. You're seeing the moon as it was when that light left its surface, bouncing off lunar dust and beginning its journey across the void to your eyes. If the moon suddenly vanished, poofed out of existence in an instant, you wouldn't know for over a second. You'd keep seeing it, a ghost image from the past, until the last photons completed their journey. The sun is even more dramatic. That warm sunlight on your face, 8 minutes and 20 seconds old. The sun could explode right now, this very instant, and you wouldn't see it happen for another 8 minutes. You'd be living in a doomed world, orbiting a star that no longer exists, and you'd have absolutely no idea. For 8 glorious, ignorant minutes, life would continue as normal. Then the sky would erupt in the most spectacular and terrifying display humanity would ever witness. And shortly after, well, let's just say your concerns about seeing the past would become pretty academic. But let's go further, much further. Look up at the night sky and find the constellation Orion. See that bright red star in the upper left, the one marking the hunter's shoulder? That's Betelgeuse, and the light you're seeing from it left that star roughly 550 years ago. When those photons began their journey across the cosmos, Columbus hadn't even reached the Americas yet. The Renaissance was in full swing in Europe. The Aztec Empire was at its height, and a star hundreds of light years away was emitting light that would eventually enter your eye in the 21st century. Think about what that means. Betelgeuse might not even exist anymore. Astronomers suspect it's nearing the end of its life cycle and could go supernova at any moment. It might have already exploded. Could have happened yesterday, could have happened 300 years ago. We simply don't know and won't know until the light from that explosion finally arrives. The Betelgeuse you see tonight is a historical artifact, a snapshot from an era when your ancestors 17 generations back were just figuring out that Earth wasn't the center of everything. Now, imagine you're in our spacecraft and you've been accelerating away from Earth for weeks. Look back at our home planet through your telescope. Focus on a city, on the people moving through streets. Here's where things get really weird. Because of the increasing distance, light from Earth is taking longer and longer to reach you. If you've traveled far enough, you might be watching events that happened minutes, hours, or even days ago, depending on your distance. But it gets stranger, much stranger. And this is where the optical effects we discussed in part 1 start combining with something else. Something that fundamentally changes your perception of time itself. Doppler effect. While moving away from Earth, you've experienced the Doppler effect countless times, even if you didn't know what to call it. Picture an ambulance racing down the street, siren wailing. As it approaches you, that siren has a high-pitched, urgent quality. Then it passes, and suddenly the pitch drops, becoming lower and more drawn out. The siren itself hasn't changed. The ambulance isn't playing to different tones. What's changed is your relative motion to the sound source. When the ambulance moves toward you, sound waves get compressed. Each wave catches up a little bit to the previous one before reaching your ear, bunching up the sound and increasing its frequency. You perceive this as a higher pitch. When it moves away, the opposite happens. Waves get stretched out, reaching your ear more slowly, decreasing the frequency. Lower pitch. This is the Doppler effect for sound, and it's happening constantly in the world around you. Light does the exact same thing, but instead of changing pitch, it changes color. Light is an electromagnetic wave, and when the source of that light is moving relative to you, its wavelength shifts. Move toward a light source, and the waves compress, shifting toward blue. Move away, and they stretch, shifting toward red. This is called redshift and blueshift, and it's one of the most important tools in all of astronomy. Back in your spacecraft, accelerating away from Earth at tremendous speed, this effect is becoming impossible to ignore. Look back at Earth through your instruments. The planet's light, normally a balanced mix of all visible colors, is shifting noticeably toward the red end of the spectrum. Earth is taking on a crimson hue as if being viewed through a deep red filter. But the color shift is just the beginning. Remember, light is also how we perceive time passing. Clocks on Earth are ticking, sending out light signals with each tick. Your sophisticated instruments can detect these signals, these temporal markers broadcasting into space. And here's the mind-bending part. Those ticks are arriving more and more slowly. Imagine a clock on Earth that flashes a light once per second. Perfectly regular, like a cosmic metronome. When you were stationary relative to Earth, you'd see one flash per second. Makes sense. But now, racing away at high speed, each successive flash has to travel a bit farther to reach you. The first flash might take 10 minutes to arrive. The second flash, emitted 1 second later from Earth's perspective, has to travel that same 10 minutes, plus the additional distance you've covered in that time. So it arrives more than 1 second after the first flash from your perspective. The faster you go, the more pronounced this becomes. At 10% light speed, those 1 second Earth flashes might arrive every 1.1 seconds. Not too dramatic. At 50% light speed, they'd arrive significantly slower, maybe every 1.7 seconds. At 90% light speed, Earth's clock would appear to be ticking at a fraction of its normal rate, each second stretching into multiple seconds from your perspective. This is the Doppler effect acting on time itself. Earth hasn't slowed down. The people there aren't moving in slow motion in any absolute sense. But from your high-speed, receding reference frame, the light carrying temporal information is being stretched out, making everything appear to happen in slow motion. Zoom in with your telescope and watch people walking down the street. They'd look like they're wading through invisible molasses, each step taking what seems like an eternity. Watch the clouds drift across Earth's skies. They'd appear nearly frozen, crawling across the atmosphere at a glacial pace. Even fast-moving objects, cars racing down highways, jets screaming through the air, would all appear sluggish and dreamlike. But here's the critical thing. This is still an optical effect. It's about how light reaches you, not about time actually passing differently. If you turned around right now and headed back to Earth at the same speed, you'd catch up with all those delayed light signals, and everything would speed up dramatically, eventually returning to normal when you arrived. Redshift and dimming. The redshift isn't just making Earth look like it's been dipped in crimson paint. It's fundamentally changing the energy of the light you're receiving. Remember from basic physics that different colors of light carry different amounts of energy. Blue light is energetic, punchy, carrying more power per photon. Red light is mellower, each photon carrying less energy. It's why blue LEDs were such a breakthrough. They required different physics to create those higher energy photons. As Earth's light redshifts, each individual photon is losing energy from your perspective. A photon that left Earth as bright blue is arriving as green. green becomes yellow, yellow becomes red, red becomes infrared, invisible to your eyes entirely. The entire spectrum is sliding downward in energy, migrating toward longer wavelengths. But wait, there's more bad news for your view of Earth. Not only is each photon carrying less energy, but you're also receiving fewer photons per second. Remember, you're racing away from Earth. In any given second, fewer light rays manage to catch up with your spacecraft than would if you were stationary. It's like trying to catch raindrops while running away from a storm. You just don't intercept as many. Combine these two effects, lower energy per photon and fewer photons per second, and Earth starts to look seriously dim. The blue-white jewel of a planet you left behind is now a faint, reddish speck, struggling to make itself seen against the blackness of space. It's still there, still emitting the same amount of light into space, but from your perspective, that light is weakened, stretched, and sparse. This dimming effect becomes exponentially worse as your speed increases. At modest relativistic speeds, maybe 20% the speed of light, Earth would look noticeably dimmer and redder, but still clearly visible. At 50%, it would be a faint red dot, requiring instruments to see clearly. At 90% light speed, Earth would practically vanish from visual observation. Its light redshifted so far into the infrared and spread so thin that only the most sensitive detectors could pick it up. Now, here's something poetic and a bit melancholy. If you could somehow maintain communication with Earth, you'd discover an interesting disconnect. Mission Control, watching you through their telescopes, would report that your spacecraft is glowing brilliantly, shifted toward blue, seemingly flooded with energy. Meanwhile, you're looking back at Earth and seeing a dim, red, fading world. Both perspectives are correct. That's the nature of relative motion. There's no absolute brightness, no universal color. Everything depends on who's moving relative to whom. This is exactly how astronomers study the universe's expansion. Distant galaxies are racing away from us, carried by the expansion of space itself. Their light reaches us, redshifted, stretched by the journey across expanding space. The farther away a galaxy is, the faster it's receding, and the more its light is redshifted. By measuring this redshift, we can calculate how fast galaxies are moving and how far away they are. Your spacecraft, fleeing from Earth at relativistic speeds, is performing the same experiment in reverse. Blue shift in the forward direction. Now, spin around in your spacecraft and look forward in the direction you're traveling. If looking backward at Earth showed you the universe in slow motion and crimson tones, looking forward is about to show you the opposite extreme, and trust me, it's spectacular. Remember those stars we talked about in part 1? The ones that were clustering together in your forward field of view due to light aberration? Well, they're not just gathering together. They're also getting seriously pumped up with energy. Every single star ahead of you is undergoing a dramatic blue shift. Their light compressed to higher and higher frequencies as you race toward them. A star that normally emits warm, yellowish light, like our sun, would start to look distinctly white, then take on a bluish tint, then shift to deeper and deeper blue. If you could somehow keep accelerating to even more extreme speeds, that light would shift beyond blue entirely, moving into the ultraviolet range, invisible to your eyes, but absolutely scorching with energy. And unlike Earth behind you, which was growing dimmer, these forward stars are getting brighter, much brighter. You're catching up with their light, intercepting more of their photons per second than you would if you were stationary. Each photon is also carrying more energy due to the blue shift. More photons, more energy per photon equals a sky that's becoming increasingly brilliant. At moderate speeds, this would be merely beautiful. The stars ahead would twinkle with an unusual blue-white intensity, like diamonds scattered on black velvet, each one somehow more vivid than you remember. But as you approach truly relativistic speeds, this beauty would become overwhelming, then dangerous, then potentially lethal. Why? Because all that extra energy has to go somewhere. Those blue-shifted photons aren't just pretty to look at. They're carrying real energy that's being absorbed by your spacecraft, by your instruments, and potentially by you at extreme velocities. The normally gentle starlight ahead of you would be blue-shifted into the ultraviolet, then into X-rays, then into gamma rays. You'd essentially be flying into an increasingly intense radiation field, like heading directly toward an X-ray machine that gets more powerful with every passing second. This is one of the lesser-known challenges of relativistic space travel. It's not just about building engines powerful enough to reach these speeds, or carrying enough fuel, or dealing with time dilation. It's also about the fact that the universe ahead of you becomes increasingly hostile from an electromagnetic perspective. Protective shielding would need to guard against not just high-speed particles, but also against the transmuted starlight itself, transformed from gentle illumination into deadly radiation by your own velocity. But there's something else happening with this blue-shifted light, something that mirrors what we saw with Earth's red-shifted signals. If you could somehow observe clocks on planets orbiting those forward stars, you'd see them ticking faster, much faster. The light carrying temporal information from those distant worlds is being compressed, bunched up by your motion toward them. A clock that ticks once per second might appear to tick twice per second, or 5 times, or 10 times, depending on your velocity. Watch aliens walking on a distant planet through an impossibly powerful telescope, and they'd appear to be moving in fast forward, scurrying about like a video played at double speed. Weather patterns would race across alien skies. Day-night cycles would flash past. Everything in the forward direction would seem to be living life in the fast lane. While behind you, Earth crawled along in slow motion. And here's where you might start to see the asymmetry of your situation really sink in. The universe isn't treating you specially. You're not at the center of some cosmic effect. Rather, your motion is creating 2 completely different views of reality. Behind you, dim, red, slow. Ahead, bright, blue, fast. 2 halves of the same universe, split by nothing more than the direction of your velocity vector. The temporary nature of optical illusion. Now, let's pump the brakes on something. Metaphorically speaking, everything we've discussed so far in this chapter, all these Doppler effects, the red shifts and blue shifts, the slow motion Earth and fast forward stars, there's a crucial point you need to understand. These are optical effects. They're about how light reaches you, how information propagates through space, how your motion relative to different sources changes your perception of them. They are not permanent changes to reality. They don't represent actual alterations to the flow of time at your destination. They're more like illusions, though that word doesn't quite capture it because they're real, measurable, physical phenomena. Maybe it's better to call them perspective-dependent effects. They're as real as the apparent shrinking of objects with distance. But just like distant objects aren't actually smaller, Earth's time isn't actually slowed down just because you see it that way. Think about it like this. Imagine you're driving away from a radio tower broadcasting music. As you speed away, the radio waves get Doppler shifted, and the music would sound lower in pitch, slower. But the music hasn't actually changed at the source. The DJ isn't suddenly playing everything at half speed. It's only your reception that's altered by your motion. Turn around and drive back toward the tower, and the pitch increases, the music seems faster. Stop your car, and everything returns to normal. The same principle applies to your spacecraft journey. Those weeks you've spent accelerating away from Earth, watching it dim and redshift, seeing its clocks tick slower and slower, none of that has permanently affected Earth. The planet is still there, spinning at its normal rate, with people living their lives in real time, completely unaffected by your observations of them. If you were to immediately reverse your engines and head back home, here's what would happen. As you slowed your outbound velocity to 0, Earth would stop redshifting and return to its normal colors. Then, as you built up speed toward Earth, you'd see a blue shift. Earth would brighten, its colors shifting toward blue. And those slowly ticking clocks would suddenly start ticking faster. Then faster still, racing to catch up with all the time you missed while flying away. By the time you arrived back at Earth, assuming you'd perfectly reversed your journey, you'd find that the total elapsed time on Earth exactly matched reasonable expectations. If your journey took 100 days according to your ship's clock, Earth would have experienced roughly 100 days as well, plus or minus the tiny corrections from relativistic time dilation, which we'll discuss in Part 3. The Doppler effects would have completely cancelled out. Every second of slow-motion observation on your outbound journey would be balanced by a second of fast-forward observation on your return. The red shift and blue shift, the dimming and brightening, all temporary phenomena that summed to 0 over the complete round trip. This is why we can call them optical effects. They're absolutely real. You can measure them with instruments, photograph them, record them, but they're not causing permanent changes to the targets you're observing. They're artifacts of light propagation combined with relative motion, not actual temporal manipulation. However, and this is a big however, don't let this fool you into thinking relativity is all just optical tricks and illusions. Because what's coming next, what kicks in when you truly push toward light speed, that's not optical anymore. That's real, permanent, and irreversible. The Doppler effects are like the warm-up act. They're interesting, they're worth understanding, but they're not the main show. The main show is time dilation and length contraction, genuine physical consequences of moving at relativistic speeds. Those effects don't cancel out when you turn around. They accumulate, they're path-dependent, and they lead to genuine, observable, permanent differences between clocks that have taken different paths through space-time. A twin who stays on Earth and a twin who takes a high-speed round trip will genuinely, physically, measurably be different ages when they reunite. That's not an optical effect. That's not about Doppler shifts or redshifts. That's about the fundamental nature of space-time itself, about how different paths through the four-dimensional fabric of our universe can have different lengths, even when they start and end at the same points. But here's the beautiful thing about understanding these Doppler effects first. They give you the conceptual framework to understand what's happening with light and observation at high speeds. They teach you that motion changes perception in profound ways. They show you that there's no single, universal perspective from which to view the cosmos. Every observer, moving at every different velocity, sees a slightly different universe, filtered through the lens of their own motion. And they prepare you for the truly mind-bending stuff that's coming. Because if you thought watching Earth's clocks tick slowly was strange, wait until you understand that those clocks are actually, genuinely, physically running at a different rate when you're in motion. If you found the redshift and blueshift effects interesting, just wait until you grasp what happens to the fabric of space itself at near-light velocities. The Doppler effects are your introduction to relativistic thinking. They're the gateway drug, if you will, to understanding that speed doesn't just change where you are, it changes when you are, how far things are, and ultimately, the very structure of reality as you experience it. So take a moment to really absorb what we've covered. You now understand why astronomers can look at distant galaxies and calculate cosmic expansion. You understand why GPS satellites need constant correction for relativistic effects, even at their relatively modest orbital speeds. You understand the fundamental principle that motion changes the way electromagnetic radiation reaches you, and through that change alters your entire perception of the universe. Are you ready to go deeper? Ready to leave the optical effects behind and dive into the real physics of spacetime? Because part 3 is where things get truly weird, where your comfortable notions of absolute time and absolute space completely fall apart, where you'll discover that moving fast doesn't just change how you see the universe, it changes the universe itself, at least from your perspective. And trust me, once you understand special relativity, once you really grasp what Einstein figured out, you'll never look at space and time the same way again. Part 3. Special relativity and physical consequences. Time dilation, the real deal. Alright, buckle up, because everything we've talked about so far, all those optical effects and Doppler shifts, they were just the appetizer. Now we're diving into the main course, the stuff that fundamentally breaks your understanding of reality. We're talking about time dilation, and this isn't some optical trick that reverses when you turn around. This is real, permanent, and absolutely verified by experiment after experiment. Here's the bombshell. Time is not absolute. There is no universal clock ticking away somewhere in the cosmos that everyone agrees on. Time passes at different rates depending on how you're moving through space. Not how you perceive time passing, but how it actually, genuinely, physically passes. Your watch, your heartbeat, your aging process. All of it can run at different rates compared to someone else, and both of you are equally correct. Let me hit you with the most famous thought experiment in physics, the twin paradox. Imagine two identical twins. Let's call them Alex and Blake. Alex stays on Earth, living a normal life. Blake climbs into our spacecraft and takes off on a high-speed journey to a distant star and back. Blake's traveling at, say, 80% the speed of light for most of the journey. When Blake returns, here's what happens. Blake is younger. Not by some tiny, negligible amount. We're talking years, maybe decades younger, depending on how long the journey took. Blake's watch shows less elapsed time. Blake has fewer grey hairs, fewer wrinkles, has experienced fewer heartbeats. Meanwhile, Alex has aged normally, living through every second of Blake's absence in full. This isn't science fiction. This is proven physics. Atomic clocks, flown on aeroplanes, even at aeroplane speeds, which are nothing compared to light speed, show measurable time differences when compared to identical clocks left on the ground. Particles created in the upper atmosphere that should decay in microseconds survive long enough to reach Earth's surface, because, from our perspective, their internal clocks are running slow due to their high speed. So what's actually happening? The answer lies in space-time itself. Our universe isn't just three-dimensional space, with time as some separate thing flowing alongside it. No, space and time are woven together into a four-dimensional fabric called space-time. Everything that exists, including you, is moving through this fabric constantly, tracing a path we call a world line. Here's the key insight. All objects are always moving through spacetime at the speed of light. Always. You're doing it right now, sitting still. How? Because even when you're not moving through space, you're moving through time. You're aging, progressing into the future at 1 second per second. That's motion through the time dimension of spacetime. But when you start moving through space, something has to give. Your total motion through spacetime stays constant at light speed, but now some of that motion is diverted into spatial dimensions. The faster you move through space, the slower you move through time. It's like a cosmic trade-off. More space velocity means less time velocity. Think of it like a car that can only go 60 miles per hour total. If you're driving straight north, all 60 miles per hour goes into northward motion. But if you turn and start driving northeast, your northward speed drops to maybe 40 miles per hour because some of that motion is now going east. Your total speed hasn't changed, just how it's distributed between directions. At normal speeds, this effect is infinitesimally small. Drive across the country at 70 miles per hour, and you'll age maybe a few nanoseconds less than someone who stayed home, completely undetectable without atomic clocks. But at relativistic speeds, it becomes dramatic. At 50% light speed, time dilation becomes noticeable. Your clock runs at about 87% the rate of a stationary clock. At 90% light speed, your clock runs at about 44% normal rate. And at 99% light speed, your clock is running at just 14% of normal. 1 of your seconds equals 7 of someone else's seconds. This is why Blake returns younger. Blake's entire journey, every moment of it, was spent moving rapidly through space, which meant moving slowly through time. Blake genuinely experienced fewer seconds between departure and return. Blake's heart beat fewer times. Blake's cells divided fewer times. Blake lived less time, and there's no way to get that time back. Length, contraction, space gets squished. Now here's where things get even weirder, if that's possible. Time isn't the only thing that changes at relativistic speeds. Space itself gets contracted. Distances shrink in the direction of motion, and this is a real, physical effect, not just an optical illusion like Terrell Penrose rotation. Imagine you're heading toward a star that's 10 light-years away. To an observer at rest, that distance is fixed. 10 light-years, about 60 trillion miles, straight forward. But to you, accelerating in your spacecraft toward 90% light speed, something extraordinary happens. That distance shrinks. The space between you and your destination literally contracts. At 90% light speed, distances in your direction of motion are compressed to about 44% of their rest length. That 10 light-year journey, from your perspective, it's now only 4.4 light-years. The universe along your path has been squeezed, like an accordion, compressed in the direction you're traveling. This isn't some measurement, error, or trick of perception. If you sent out radar signals to measure the distance, they'd confirm it. 4.4 light-years. The space is genuinely shorter from your reference frame. Someone watching you from Earth would insist the distance is still 10 light-years, and they'd be right too. Both measurements are correct in their respective reference frames. Here's what's mind-blowing about this. Length contraction makes interstellar travel potentially feasible, at least from the traveler's perspective. That star system, 20 light-years away. If you could reach 99% light speed, the journey would shrink to about 3 light-years from your perspective. You could make the trip in roughly 3 years of ship time, even though Earth would measure it as taking just over 20 years. Push even closer to light speed, and the effect becomes more extreme. At 99.9% light speed, distances contract to about 4% of their rest length. 100 light-year journey becomes 4 light-years. 1,000 light-year journey becomes 40 light-years. The galaxy itself, normally 100,000 light-years across, would be compressed to just 4,000 light-years in your direction of travel. In principle, if you could somehow accelerate to 99.99% light speed, you could cross the entire observable universe, billions of light-years, in a human lifetime from your perspective. The universe would be pancaked to almost nothing in front of you, a thin sheet of space that you'd traverse in decades of ship time. Of course, billions of years would pass in the rest frame of the universe, but you wouldn't experience that. To you, the journey would feel manageable. This is the flip side of time dilation. When time slows down for you, space contracts. They're two sides of the same relativistic coin. You can think of it as the universe's way of keeping things consistent. If your clock is running slow, you need to be able to cover distances in less time, so the distances themselves shrink to compensate. But here's the crucial thing. This contraction only happens in the direction of motion. Perpendicular directions are unaffected. If you're flying north at 90% light speed, distances to the north and south are contracted, but distances to the east and west remain normal. Space becomes anisotropic, different properties in different directions, all because of your velocity. Journey distance shortening. Let's make this concrete with an example that really drives home how bizarre this gets. Imagine there's a space station exactly 5 light-years away from Earth, sitting stationary relative to our solar system. Mission Control on Earth decides to send you there in a spacecraft capable of reaching 95% light speed. From Earth's perspective, the math is straightforward. Distance equals 5 light-years. Speed equals 95% of light speed. Time equals distance divided by speed, which works out to about 5.3 years. Earth would expect your journey to take roughly 5 years and 4 months. But let's look at it from your perspective aboard the spacecraft. As you accelerate toward 95% light speed, length contraction kicks in. That 5 light-year distance shrinks to about 1.6 light-years from your reference frame. The space station isn't 5 light-years away anymore. It's only 1.6 light-years away. The space between Earth and the station has been physically compressed. Now, you're still traveling at 95% light speed from your own perspective. So your travel time is 1.6 light-years divided by 95% light speed, which equals about 1.7 years, not 5.3 years, just 1.7 years. You experience a journey that's only about 1/3 as long in time as Earth measures. Where did those extra 3.5 years go? They didn't go anywhere. They never existed for you. Your watch, ticking away normally from your perspective, genuinely measured only 1.7 years. Your body aged only 1.7 years. You ate meals for 1.7 years. That's the reality you lived. Meanwhile, back on Earth, 5.3 years genuinely passed. People aged 5.3 years. Seasons changed 21 times. Children grew taller, got older, moved through school. Both timelines are real, both are correct, but they're different because you and Earth took different paths through space-time. This is the practical upshot of relativistic space travel. Journeys that seem impossibly long from Earth's perspective become manageable from the traveler's perspective. A 20-year journey to Earth becomes a 5-year experience for the crew at high enough speeds. A 50-year journey becomes 15 years. A century becomes 30 years. Of course, there's a catch, and it's a big one. While you're experiencing these shortened journey times, decades or centuries are passing on Earth. You could leave Earth in your 30s, travel to a distant star, and return in your 50s, having experienced 20 years of life. But Earth would have aged 200 years. Everyone you knew would be long dead. Civilization would have changed beyond recognition. You'd be a time traveler to the future, unable to go back. Relative time difference. This brings us to one of the most profound and emotionally challenging aspects of relativistic travel: the relativity of simultaneity. Events that are simultaneous in one reference frame are not simultaneous in another. Time becomes personal, frame-dependent. Your now is not the same as Earth's now once you're moving at relativistic speeds. Imagine you're halfway to that distant star, cruising at 95% light speed. You look at your calendar and see that exactly 1 year has passed since you left Earth. From your perspective, it's been 1 year. You celebrate a modest 1-year anniversary of your departure. But what's happening on Earth at that same moment? Here's where it gets tricky, because that same moment doesn't have a universal meaning anymore. From Earth's reference frame, more than 2.5 years have passed. Your 1-year anniversary corresponds to Earth being 2.5 years older. Your mother, who was 60 when you left, is now 62.5. Your nephew, who was starting kindergarten, is now finishing 2nd grade. But it's even stranger than that. The concept of simultaneity, of what's happening right now at different locations, depends on your velocity. If you suddenly accelerated to an even higher speed, your plane of simultaneity would shift. Events on Earth that you considered to be happening now would suddenly be in your past or future, depending on which direction you accelerated. This isn't about communication delays or light travel time. This is about the fundamental structure of spacetime. There is no absolute present moment that spans the entire universe. The present is local, personal, defined by your motion through spacetime. This creates some deeply weird scenarios. Imagine you're traveling away from Earth at high speed, and you look back and see Earth as it was years ago due to light travel time. But the actual now on Earth, the events happening simultaneously with your current moment from your reference frame, is even further in the future than the present moment in Earth's reference frame. You're literally living in a moment that's offset from Earth's moment, and the offset changes depending on your velocity. For someone planning a relativistic journey, this has profound implications. You're not just traveling through space. You're not even just experiencing time dilation. You're fundamentally divorcing yourself from the temporal flow of the civilization you left behind. Every second you spend at high velocity increases the gap between your timeline and theirs. Real versus optical phenomena. Let's take a moment to really crystallize the difference between what we discussed in part 2 and what we're talking about now, because this distinction is absolutely crucial. The Doppler effects, the red shifts and blue shifts, the apparent slowing or speeding of distant clocks, those were optical effects, real, measurable, but reversible. They depended on how light was reaching you, and they'd cancel out over a round trip. Time dilation and length contraction are different beasts entirely. These are physical effects that arise from the structure of spacetime itself. They don't depend on how you're receiving light. They don't cancel out when you turn around. They accumulate, they persist, they're path-dependent. Think of it this way: Doppler effects are like watching a movie at different speeds. You can watch it in slow motion on the way out, then fast forward on the way back, and you'll still see the whole movie, just in a different order. But time dilation is like actually living less time. You're not watching the universe at a different playback speed. you're genuinely experiencing fewer moments of existence. An astronaut who goes on a high-speed round trip doesn't just see Earth's clocks ticking fast on the return journey to balance out seeing them tick slow on the outbound journey. The astronaut actually, genuinely, physically, ages less. Fewer biological processes occur. Fewer thoughts are thought. Less time is lived. That's not an optical illusion. That's reality. The same goes for length contraction. When space contracts in your direction of motion, it's not like objects ahead of you just look smaller. The journey actually requires you to traverse less distance. Your odometer, if you had a cosmic odometer measuring distance through space, would show fewer miles, kilometers, light years, whatever units you prefer. This is special relativity in a nutshell. Motion through space affects the flow of time and the measurement of distance, not as optical tricks, but as genuine features of how spacetime works. Einstein's insight was recognizing that space and time are not separate, absolute entities. They're interwoven, relative, observer-dependent. The only absolute is the speed of light itself, and everything else flexes and bends to maintain that constancy. And here's the beautiful, terrifying thing. This isn't speculation. This is experimentally verified to absurd precision. Particle accelerators see relativistic effects every single day. GPS satellites have to account for time dilation or they'd accumulate errors of miles per day. Cosmic ray particles exist far longer than they should because their internal clocks run slow from our perspective. We're not theorizing here. We're describing reality. Your intuition might scream that this is impossible, that time must be absolute, that distances must be fixed, but the universe doesn't care about your intuition. This is how it works, confirmed by over a century of experiments, and it's not changing just because it seems weird. So as our spacecraft continues its acceleration, pushing closer and closer to light speed, you're not just experiencing stranger and stranger optical effects. You're literally restructuring your relationship with spacetime itself. You're becoming a being for whom time flows differently than it does for the rest of humanity. You're experiencing space as contracted, distances as shortened, journeys as briefer, and the closer you get to light speed, the more extreme these effects become. But can you actually reach it? Can you hit that ultimate speed limit? That's the question burning in your mind now, and answering it will take us into even stranger territory. Because the answer reveals something fundamental about the structure of our universe, something that sets an absolute limit on motion itself. Ready to find out why light speed is truly unreachable? Part 4. The limits of light speed and unreachability. The absoluteness of light speed. Here's the ultimate truth about our universe. The one rule that cannot be broken, bent, or circumvented. Light speed is absolute. Not just fast, not just really fast, but fundamentally, unchangeably constant from every possible perspective. No matter who you are, no matter how fast you're moving, light always travels at exactly 186,000 miles per second relative to you. Think about how insane that is. You're standing still. You measure light speed, 186,000 miles per second. Now you jump in a spacecraft and accelerate to half light speed. You measure light again. Still 186,000 miles per second. Not faster, not slower, exactly the same. You push to 90% light speed. Measure again. Still the same speed. This defies every intuition you have about motion. If you're on a train moving at 50 miles per hour and you throw a baseball forward at 50 miles per hour, someone watching from the platform sees the baseball moving at 100 miles per hour. Velocities add. That's how the world works, right? Wrong. That's how the slow speed world works, where relativistic effects are too small to notice. But at high speeds, velocities don't simply add. They combine in weird ways that always keep light speed constant. Chase a light beam at 99% light speed, and from your perspective, that light beam is still escaping you at full light speed. Not 1% light speed, not some tiny crawling velocity. Full speed. This is what Einstein realized back in 19-0-5. Light speed isn't just another velocity. It's the conversion factor between space and time, the fundamental speed limit woven into the fabric of spacetime itself. It's not that light happens to go this fast. It's that this speed represents the maximum rate at which cause and effect can propagate through the universe. Photons, the particles of light, travel at light speed because they have zero mass. They literally cannot travel any slower. But nothing with mass can reach that speed. No matter how much energy you pump in, the universe has a speed governor built in, and it's absolute. The infinite acceleration paradox. So what happens if you just keep accelerating? You've got unlimited fuel, unlimited time, engines that never quit. Surely eventually you'd hit light speed, right? You'd have to. Just keep pushing, keep adding velocity, and eventually you'd get there. Except you won't. Ever. Here's why, and it's beautifully, maddeningly elegant. As you accelerate closer and closer to light speed, something strange happens to your mass, or, more accurately, to your energy. The faster you go, the more energy it takes to accelerate you further. Not just a little more, exponentially more. At 50% light speed, you need a bit more energy to gain another 1% of velocity than you did at 0. At 90%, you need significantly more. At 99%, you need vastly more by the time you reach 99.9% light speed. Accelerating that final 0.1% takes more energy than accelerating from 0 to 90% took. And the closer you get, the worse it becomes. That last 0.01%. More energy than all previous acceleration combined. The last 0.001%. Even more. It's an asymptotic curve, approaching but never reaching the ultimate limit. In fact, to actually reach light speed, to push that last infinitesimal fraction of a percent, would require infinite energy. Not just a lot of energy. Not more energy than exists in the solar system or galaxy. Literally infinite energy, which doesn't exist, which can't exist, which means you can never, ever reach light speed. From your perspective inside the spacecraft, your instruments would show continuous acceleration. Your engines are firing, you're burning fuel, you're gaining velocity relative to where you started. 1 year of constant acceleration, 2 years, 10 years, your speedometer climbs higher and higher. But here's the cosmic joke. You never feel like you're approaching light speed. Why? Because from your reference frame, you're always stationary. You can't feel absolute velocity, remember, only acceleration. And light, no matter how long you've been accelerating, still races away from you at full light speed. Shine a flashlight forward. The light beam leaves your ship at 186,000 miles per second relative to you. Fire your engines for another year. Shine the flashlight again. Still 186,000 miles per second. The universe refuses to let you catch up. Extreme field of view contraction. But even though you can never reach light speed, you can get arbitrarily close. And as you do, as you push to 99.9, 99.99, 99.99%, the optical effects we discussed in part 1 become absolutely extreme. Your field of view doesn't just contract, it collapses toward a single brilliant point directly ahead. Remember light aberration, how stars seemed to gather forward as you accelerated. At near-light velocities, this effect goes into overdrive. Stars from all directions, even from behind you, appear to be shifted forward. Your entire view of the cosmos compresses into a shrinking circle ahead of you, surrounded by expanding darkness. At 99.9% light speed, stars that were 90 degrees to your side, directly perpendicular to your motion, now appear to be 30 degrees ahead. At 99.99%, those same stars appear only about 8 degrees from your forward direction. The universe is being squeezed into an ever-tightening cone in front of you. Eventually, if you kept accelerating close enough to light speed, your entire visible universe would compress into a tiny, intensely bright spot directly ahead. Everything else would be black, not dark, not dim, utterly black. The light from behind you can never catch up. The light from your sides is so severely aberrated forward that the rear hemisphere of space is completely invisible. And that bright spot ahead, it would be incredibly intense, almost blinding. Remember, if light from stars ahead gets compressed to higher energies as you approach them at relativistic speeds, at extreme velocities, ordinary starlight would be blue shifted into ultraviolet, then X-rays, then gamma rays. You'd be flying into what amounts to a cosmic blowtorch of radiation. Extreme optical effects. The aberration and blue shift combine to create something that looks utterly alien. Imagine the entire night sky with its billions of stars, countless galaxies, nebulae, and cosmic structures, all compressed into a circle maybe 10 degrees across, blazing with unimaginable intensity, a cosmic searchlight beam drilling through the darkness, with you at the center, racing toward it. Colors would be completely wrong. Cool red stars would appear blue-white. Yellow stars like the sun would glow deep violet or beyond visible range entirely. The cosmic microwave background radiation, normally invisible at a few degrees above absolute zero, would be blue shifted into visible light. The afterglow of the Big Bang itself would become visible as a dim background glow surrounding that forward intensity. Behind you, absolute nothing, a void, not even the faint glow of distant galaxies. All that light is chasing you, redshifted into oblivion, stretched to radio waves and beyond, never catching up to your fleeing spacecraft. You'd have created your own personal event horizon of sorts, a rear sphere from which no light can reach you. The Doppler effects would be pushed to absurd extremes too. Objects ahead would appear to be evolving at incredible speeds. Watch a planet orbiting a distant star, and you might see it complete orbits in minutes or seconds, time compressed by your motion toward it. Behind you, if you could somehow see anything at all, time would be frozen, approaching zero velocity, the universe's contracted experience. From your perspective, the universe itself would be radically transformed. Length, contraction, pushed to extreme levels, would compress all of space in your direction of motion into a thin pancake. A galaxy 100,000 light-years across would be flattened to maybe 100 light-years thick in your art direction of travel. This means journeys that should take astronomical amounts of time become manageable. At 99.99% light speed, a trip across the entire Milky Way, normally a 100,000-year journey at light speed, would take only about 140 years from your perspective. Still a lifetime, but technically possible for a human. Push even closer, say 99.999%. and that same journey takes 14 years. Suddenly, crossing the galaxy becomes feasible. You could leave Earth in your 20s, reach the other side of the Milky Way, and return in your 50s, having spent 30 years traveling. Of course, 200,000 years would have passed on Earth, but you wouldn't have experienced that. You'd have lived just 30 years. This is the ultimate weird fact about near-light speed travel. The faster you go, the less time the journey takes from your perspective, even though it takes more time from everyone else's perspective. The universe becomes smaller, distances shrink, journeys shorten, but only for you. Everyone else still measures the same vast distances, still waits the same long years for your return. In theory, with enough acceleration, you could cross the observable universe, billions of light years of space, in a single human lifetime. The entire cosmos would be contracted to a thin sliver in front of you, a few light years thick, traversable in decades. From Earth's perspective, billions of years would pass. Entire civilizations would rise and fall. Stars would be born and die. But you'd experience just a few decades of life. This is both the promise and the curse of relativistic travel. You could explore the cosmos, witness sights no human has ever seen, visit alien worlds separated by impossible distances, but the price is steep. Everyone you've ever known would be dead. Your entire civilization would be ancient history. You'd return to find Earth transformed beyond recognition, assuming it even still exists. And here's the final, inescapable truth. You still couldn't reach light speed. You could get close enough that the remaining difference is measured in infinitesimal fractions of a percent. You could experience the universe as a compressed, brilliant, streaking blur. You could cross galactic distances in years of ship time. But that final threshold, that absolute limit, would remain forever out of reach. The universe has a speed limit, and it's not just a suggestion. It's woven into the fundamental structure of reality itself. Breaking it isn't just technologically impossible, it's logically impossible. It would require infinite energy, infinite time, or a complete rewriting of physics itself. Or would it? Because there might be one loophole, one trick that lets you sidestep this cosmic speed limit without actually violating it. Not by moving through space faster than light, but by moving space itself. And that's where things get truly science fiction, truly speculative, yet mathematically intriguing. That's where warp drives come in, and trust me, the universe they create is even stranger than anything we've discussed so far. Ready for the finale? Part 5, Warp Drive and Bending Spacetime, Methods for Exceeding the Light Speed Limit. So we've established that nothing can move through space faster than light. That's ironclad, unbreakable physics. But here's the loophole that science fiction writers have been exploiting for decades. What if we don't move through space? What if we move space itself? General relativity, Einstein's theory of gravity, tells us that space-time is flexible. Massive objects bend it, creating what we experience as gravity. Black holes warp it so extremely that not even light escapes. The universe's expansion stretches it, carrying distant galaxies away from us faster than light. That last part is crucial. Space itself can expand faster than light without violating relativity. The speed limit only applies to objects moving through space, not to space moving relative to other space. So theoretically, you could create a bubble of space-time around your spacecraft, compress space ahead of you, expand it behind you, and surf that wave faster than light. Your ship wouldn't be moving. It would be stationary inside its bubble. But the bubble itself, the warped space-time carrying your vessel, could travel at any speed, 10 times light speed, 1,000 times, 1,000,000 times. No physical law prevents it. This is the warp drive concept, popularized by Star Trek, but actually rooted in legitimate physics equations published by physicist Miguel Alcubierre in 1994. The math works. The equations balance. On paper, it's possible. Warp drive theory. Alcubierre's warp drive would create a region of contracted space in front of your ship and expanded space behind it. Imagine space as a rubber sheet. Ahead of you, the sheet bunches up, bringing your destination closer. Behind you, it stretches out, pushing your starting point farther away. The ship sits in a flat region between these two zones, experiencing no acceleration, no stress, no time dilation. You're essentially standing still while space moves around you. From inside, you'd feel nothing unusual. No crushing forces, no relativistic effects, just smooth sailing. The brilliant part: the bubble moves through space, carrying you along. An outside observer would see your ship streaking past, faster than light, but you're not actually moving relative to your local space-time. You've found the ultimate loophole. Science fiction enthusiasts immediately recognized this as vindication. See, warp drive isn't fantasy. It's real physics. Sort of. Because there's a massive, universe-sized catch that makes this whole concept probably impossible in practice. Practical impossibility. Here's the problem. Creating this warp bubble requires exotic matter, specifically matter with negative mass and negative energy density, not antimatter, which has positive mass. We're talking about matter that has less than zero mass, matter that would fall up instead of down, matter that would push instead of pull gravitationally. And here's the kicker: we've never observed negative mass anywhere in the universe. Not in particle accelerators, not in deep space, not in quantum experiments. It might not even exist. It might be physically impossible, forbidden by deeper principles we don't fully understand yet. Even if negative mass exists, the amount required is staggering. Early calculations suggested you'd need more negative mass energy than exists in the entire visible universe just to create a small warp bubble. Later refinements reduced that estimate. But we're still talking about energy scales far beyond anything humanity could conceivably harness. So while the mathematics allows warp drives, practical reality almost certainly doesn't. It's like discovering that the equations technically permit time machines, then realizing you'd need to harvest the energy output of an entire galaxy to build one. Still, let's indulge the fantasy. Let's imagine we somehow solved these problems and built a working warp drive. What would we actually see? Ready for the strangest view yet.